Welcome everyone. In today's class we are going to discuss about path based scheduling. So, if you remember we have in the start of this scheduling we have discussed that we are going to take the program, because I have given a program, but what we did is actually break that program into basic blocks, right. And whatever the scheduling algorithm I have discussed so far, it is basically scheduling of that basic block, one basic block at a time. Right. So, that means we are not considering the control structure of the behavior, but taking only the basic block of operations where there is a sequence of operations are there, and we try to identify the minimum number of time step or minimum number of resource under timing constraint. Those kind of problem we have solved, and finally, we will get the schedule for each basic block, right. And then how the final behavior will look like is combining this basic block into one, right. So, just to give an example, suppose I have one program like this. So, you have a say there is a basic block here, then there is a condition here, and say right. So, this is the if else, right. So, and then you have something here. Okay. So, the way it is now discussed is that if there are say 10 operations here, right. So, there are 5 operations here and there is a 20 operations here and there are 10 operations here, right. So, these are the number of operations are there. And what we have done so far is that I take this basic block at a time and say I have scheduled in say 4 timestamp, right. And then I schedule this into say 2 timestamp, this is in 4 timestamp, or say 5 timestamp, and this is in say 3 timestamp, right. So, and how do we combine this is basically for this schedule is like this, right. So, there are 4 timestamp. So, this is my basic block 1, then I have a condition. So, here I have 2 state and I have 5 state here, right. So, then I will combine this will into this, and then this will be my 3 state for this. Okay. So, this is a basic block 1 B 1, this is basic block 2, this is basic block 3 and basic block 4, right. So, this is B B 1, this is my B B 2, this is my B 3 and this is B 4. Right. So, I did all these basic block means sequence of operation, there is no control flow there. So, I take one basic block at a time, I do a best scheduling to solve this problem, and then I combine each basic block into this control structure, and this is my final controller FSM, right. So, this is my controller FSM, right. So, this is what we have done, and then we know what are the operations is happening in every state, and based on that we will construct the data path, right. That is what the way we have discussed so far. Now, here you try to understand, obviously problem here is so one of the drawbacks here is like I have come up with very efficient algorithm, very optimal algorithm, but it cannot solve the, it only applicable to a one basic block, right. It does not you cannot merge this scheduling with this, right, because they are taken independently, right. So, 2 basic block scheduling cannot be combined together, because I have not taken them together. As a result, whatever the optimization you do here, the final latency of the design is not something optimized across basic block. It is optimized within basic block, it is not optimized across basic blocks, right. So, in the path based scheduling, it try to solve that problem, right. So, it try to achieve minimum latency by try to share the operation across basic block. So, how it takes the code. So, instead of taking this basic block, what it does now, it takes a path, right. So, how many paths are there? You have 2 paths, right. So, this is one path. So, this is my path 1 and this is another path, right. So, there are 2 paths. Okay. Obviously, you can ask me what will happen to the loop, I will come to that point. So, there are 2 paths now, right. So, you now think about that I am going to take the path P 1, and how many operations are there? 10 plus 5 plus 10, 25, right. So, now there are 25 operations in path 1, and in path 2 I have 10 plus 20 plus 10, 40 operations, right. So, now what we can do is I am going to schedule path 1 independently. Now, if we try to find out the minimum number of timestamp needed for path 1, obviously since I can have a sharing of timestamp between operations of two different basic blocks, because if they are not data dependent, I can actually schedule this probably in say 7 timestamp, okay. And then and this and say this particular timestamp is basically say it is scheduled in 10 timestamp. So, that something is understood, and now you think about that now it is 10 timestamp. So, earlier you think about that it is 4 plus 2 plus 3, right. So, 6 plus 9 timestamps, right. If you take this path, it is basically taking say 9 timestamp, and this was taking say 4 plus 5 plus 3 12 timestamp. Now, it is taking only 7 and 10, which is less than the actual timestamp it was taking in the basic block. So, the basic point here I try to convey is that if you take the paths at a time, since there are some operation which is basically there is no dependency among operations, you can parallelize these operations, you can schedule them in same timestamp. So, the number of timestamp needed to schedule this behavior will be much lesser than the number of timestamp needed if you go by basic block based scheduling. Okay. So, the path based scheduling is actually try to do that thing. Okay. So, as I mentioned here, the basic block based scheduling schedule the each basic block one by one, right. In path based scheduling, we schedule the path one by one. Okay. So, that is understood that I will identify the paths and I am going to schedule the paths one by one, right. And then in basic block based scheduling, what we have done? We basically combine this schedule of all basic block together, right. So, combine means is basically just creating this FSM that I have already explained. So, similarly, in path based scheduling, I have to combine the schedule of two paths, right. So, for example, here you see I have mentioned that there are 7 states here, right. Say probably it has a 7 state, and in path 2 I have 10 states, right. Right. So, obviously, the number of state together will be 10, because it will be max of this, right. So, for path based scheduling, similarly I have every path we have I found the minimum of, schedule for each path, I have to combine them. So, how to combine these two paths together, that is something we are going to discuss in this class, but the basic approach is similar to the basic block, that where we are taking one basic block at a time, schedule, and then you combine the results. Here you identify the paths, schedule the paths independently, and then combine the schedule of the paths, right. That is the overall path based scheduling algorithm. Okay. So, the overall objective of this path based scheduling is the reduction of the latency. So, whatever the latency can be achieved through this basic block based scheduling will be much higher than this path based scheduling, because in the path based scheduling I have an opportunity to share timestamp across basic blocks, right. So, the primary objective of this path based scheduling is to minimization of the number of control state to schedule the branches without violating the resource and timing constraint, right. So, that is the objective. I understood that I want to schedule the whole behavior in minimum number of timestamp, so without violating the resource and timing and other constraint, right. So, for path based scheduling, one important factor is operation chaining. Okay. So, that something is quite used in path based scheduling. So, let me explain that operation chaining now. So far suppose you have an expression a plus b plus c, right. So, the way we have discussed earlier that I will do say d equal to, I will break it into 3 address form, right. So, the way I will do is basically I will do a equal to a plus b, and then say out equal to d plus c. So, this is how I just break the a plus b plus c, right. So, say out equal to a plus b plus c is there. So, I can break into this form. So, this I have argued earlier that I will going to do it because I want to do this operation, individual operation I want to schedule, right. If you try to schedule everything together, my delay will more, right. But since this operation, this path based scheduling, my objective is to schedule everything in minimum number of timestamp. So, here probably if my timing permits, probably I am going to do this a plus b plus c in the one clock, right. So, that means I have to chain to adder, right. So, that is what is called operation chaining. So, this is there because if say you already know that things, that if there is a multiplier which is say a it is much complex operation than a adder operation. So, if you try to combine this, if you schedule one multiplier and one adder in the same time stamp, some of the time this adder will remain idle. So, you can, instead of doing one addition one time, you can actually perform two addition operation in chain in the same time, right. So, that is what is called operation chaining. So, let me explain in the context of A plus B plus C. So, as I mentioned that in normal whatever you have discussed, that I am going to do this A plus B in time stamp 1, right, and then in A plus B plus C, and then the D plus C in time stamp 2, right. So, this is 2 time stamp to perform this operation. But if you do this in 2 time stamp, I need only one adder, right. I need only one adder. I can actually share the adder between these 2 operations, because they are actually happening in 2 different time stamp, and this will be the architecture, right. So, basically I need a mux at the input of the adder. So, this is my adder, and at the input I need a mux. So, in the first time stamp I am going to do A plus B, in the next time stamp I am going to do D plus C, right. I am going to do D plus C. So, I am going to multiplex this input, and then output will, one time it will go to D and next time it will go to E or out. Okay. So, that is what is going to happen in normal scenario. In operation chaining, so as I mentioned that there may be say some another big multiplier schedule here, which is say 30 millisecond, say 30 nanosecond, and this adder is only 10 nanosecond. So, I can easily do these 2 operations at the same clock, because otherwise the adder will remain idle for 20 nanosecond. So, here I am not performing this 2 addition operation in 2 cycle, rather I am doing the whole thing in same cycle S1, right. And what I am doing here, so I am going to put a adder here, and the output of adder is not going to any register, it is going to the another adder, right, and this is going to happen in the same clock. The architecture you understand here, that I have A plus B adder here, and then the result is coming here, and I am just doing this, I am adding with C, and then directly I am going to update E. So, I do not need to store the intermediate results D into some register. So, this is something called operation chaining. Okay. And operation chaining is nothing new, and it is nothing related to only path based scheduling. You can actually do the same thing in normal scheduling as well. But so far the way we have discussed the scheduling, we do not consider operation chaining so far. But in path based scheduling, this is very obvious, because our objective is to schedule everything in minimum number of time stamp, right. So, if the timing satisfied, if the target clock is 30 nanoseconds and there are 2 adder in chain, this path based scheduler always will schedule them in series, so that they can be scheduled in the same clock. Since the objective of this path based scheduling is to identify the minimum of time stamp, so it does not look into the resource overhead, because here you can see if I schedule these 2 operations in 2 different time stamp, I need only one adder. Here I need 2 adders, because they are going to happen in the same clock, right. So, I need 2 adder, but because this path based scheduling does not look into that aspect, it will do that. But in other sense, if you say that I have only one adder, it will not do this, right. It again it will give you these results. So, it is not that, I mean, to precisely state that, it depends on your resource constraint. So, if you say that I have only one adder, it will not generate this resource, but it is going to generate this particular schedule, okay, where I can actually schedule this 2 operations in 2 time stamp, and hence I can share that. Okay. So, but in general, if timing constant satisfy, resource constant satisfy, we try to schedule as many as operations in chain as possible without violating the resource and timing constraint. Okay. So, that something is operation chaining, and which is quite useful in path based scheduling, as I argued that here objective is to minimization latency without violating my constraint. Okay. So, now if I just define this path based scheduling problem, so I have given this graph my overall program, and I have given a set of constraint. So, I am going to talk about what are the constraint, as I mentioned the resource constraint, timing constraint, right, everything we will give together, right. And then I am going to schedule this operation, all the operations in G, such that all possible longest path I am going to talk about that. So, you can think about the paths can be scheduled in minimum number of control states. So, this is very important. Here I want to schedule everything in minimum number of control states, okay, and without violating the constraint. Okay. So, this is my path based scheduling problem. So, what are the steps to be performed in path based scheduling? So, obviously, you have given a program, you have to represent them as a control and data flow graph, that we already understood, and the dependency probably using the DAG within the basic block. And as I mentioned here, I have to schedule the paths one at a time, right. So, I have to identify the paths, and this paths called longest path. I will talk about what is longest path. So, first thing is that you identify the paths, possible paths in the program, okay, and then you basically take each path and you schedule it. So, here it is scheduled using AFAP algorithm. Okay. So, this is not ASAP or ALAP, it is AFAP, as fast as possible. So, as our target is to execute as fast as possible. So, operation chaining is very important in this context. Okay. So, this is a new algorithm I am going to talk about, that what is AFAP algorithm. It is not ASAP or ALAP, it is AFAP. Okay. And then you combine the schedule of all paths and into one schedule, and then you build the data path and controller FSM. Right. So, these are the 5 steps to be performed in the path based scheduling algorithm. Okay. So, let us try to go into each steps at a time. So, the first problem is that you basically have the program, you represent them using paths. Okay. So, how to do that? What we do, we actually construct a special kind of CDFG here. So, you have the programs, and then what you do, you basically you have every operation you are going to represent by now a states. Okay. Every operation is a state now, and whenever there is a control flow or data flow, you are going to add an edge. Okay. So, if there is a if else, so it is going to be edge like this. Okay. Okay. So, this is something I am going to do that. So, I have each node is designated operations, and control this edge designates the controller data dependencies. Okay. Since these operations are actually, you can see here I am actually putting one operation at a time. So, the data dependency already taken care. So, this edge is basically saying there is a kind of data dependency or control dependencies. Okay. So, now we actually assume here all operations are single cycle, but again you can actually break a multi-cycle operation into multiple single cycle operations. So, for example, to give this idea that if say there is a multiplier which is a 3 cycle operation, I can actually in my graph I can just represent this multiplier as like this. Say I have, so this is my multiplier. So, I can just say this is nothing but 3 operation in chain, small operation in chain. So, M1, M2 and M3, and there will not be no other edge in between. So, this is just, so if there are say 2 inputs are coming, 2 inputs will come here, and if it is going to 2 other output, it will go like this. So, I can just represent this multiplier using 3 small multiplier of single cycle. So, I can handle multi-cycle operation, but just transforming a multi-cycle operation into those many single cycle operations. Okay. So, basically just to explain this, so suppose I have given this behavior where there is a for loop here, outer loop, and these are the operations, right. So, and there is a if else, you can see here there is a if else, and there is a while loop here. Okay. So, how to represent this as a CDFG here? So, I am going to put one operation. So, there are how many operations are there? 10 operations. So, I am going to put each operation as each node, right. So, this is operation 1, this is operation 2, 3, 4, 5, 6, 7, 8. So, for each line or each line there is a node here. So, that is done, and then since there is a control flow here, because after this operation 1, this operation 2 to be executed, I am going to add an edge here. Okay. Similarly, I am going to add an edge here, and so after this node 3 there is a if else. So, I am going to add a if else here, and this is the basic block corresponding to this is 5, and this will come to here, right. So, you can understand that, and this while loop there is no body, it is basically a while one, right. It is a busy wait. So, I just have a loop here, and then the 7, 8, 9, 10 these operations will be there, and there is a back edge. Okay. So, because this of this for loop. Okay. So, this is what the CDFG representation of the program. So, that we have done first. Okay. This is my step 1, you convert the code into CDFG and data flow graph, right. So, that is something is done here. So, what is the longest path? So, the path in the CDFG from a node V to another node without any successor. So, this is very important that it is, there may be many paths, right. So, you can think about that this is also a path, right. So, this is also a path, but I am not going to consider this kind of path. I am going to consider only path which start from some node, it can be from any node, but it will end to some node where there is no other further transitions, right. So, that means I cannot take, I am not going to take any path of this length, any sub path, this is a smaller path, but the longest path is those path will start from any node. It is not that it has to start from the start node, it can start from any other node. I am going to come on to that from where it can start, and then it will always end to some node where further there is no successor, right. So, this is the kind of last state in your program. So, those are the longest path. Okay. Now, the question is that the first thing is you identify this program, you convert into this, and now the question is that how do you identify the longest path and what are the longest path we have to identify. Okay. So, here you have to understand that if for if else it is fine, but there is a if there is a loop. So, that loop is going to iterate many times, right. So, the important point here is that the longest path obviously will start from the end state and that will going to end in the end state. Okay. But I should also consider path that is starting from a loop point, loop starting point. Okay. Because if I do not consider such paths, then the repetition of the loop body will be lost. Okay. So, we need to consider two type of paths, the paths that are starting from the start node and ending some node where there is no successor node, and also the paths that are starting from the loop starting point. So, there are two types of longest path here. So, the paths either start from the start node or the loop node and ends at the in a state which has no successor. Okay. So, these are the paths I am going to consider. Longest path are defined as the paths that are starting from the start node and the loop node. Okay. So, before that one pre-processing to be done here. So, because this loop can create infinite number of paths, so what I am going to do, I am going to remove these loops, okay, the back edge. It is not I am going to remove the loops, rather the back edge, and I will keep that information handy for me for future use. Okay. So, there are two loops here. So, there is a one loop is 7 to 7. So, I am going to just keep that my loop 1 is basically 7 to 7. So, I will just put the back edge 7 to 7. And there is a loop another, there are actually two loops, right. So, this is one loops and this is another loops, right. So, there are two loops here, but for both the loops this is the back edge, right. So, if I just remove this edge, I can remove the loops, right. So, I will just say there is another loop for which there is a back edge from 10 to 1. Okay. So, this is what I am going to do, right. So, what I am going to do, I will just keep two information. I have loop 1 for that back edge is 7 to 7 and there is a loop 2 for as the back edge from 10 to 1, right. So, I am going to remove this edge and this edge. Okay. So, I am going to remove this edge and my revised CDFG looks like this. So, this is done to avoid having infinite number of paths, longest path. Okay. So, if I have this, so you will come here and then it will go on. So, it might have any infinite number of paths, right. So, just to avoid that, I remove the back edge, but since I am starting my longest path again from the loop point. So, it will not create a problem, because I mean eventually I know that this is the starting point, and from there if I just add the back edge, whatever the schedule I am going to get, if I add the back edge, it will make sure that it will actually happen in loop. I am going to discuss that things in detail in subsequent part, but let us assume that I am going to remove the back edge before identifying the longest path. Okay. So, now if you just remove this and then you get this, how many longest path are there, right. So, obviously, if you start from this node, so this will be one longest path. So, this is another one, you start from here, you go to the else branch, right. So, that this is my path 2, and as I mentioned 7 was the loop point. So, I am going to start the third path, which is from this to this, right. So, there are P1, P2 and P3, and so basically in this behavior there are 3 paths. Okay. So, that is what given by this. So, this is my path 1, this is path 2 and this is path 3, which is starting from 7 to. So, this is something understood. So, now the interesting things here, you see that here that loop was busy waiting, there is no operation inside this, right. So, now you take an let me take a scenario where if there is some operation inside the loop, how many paths I will identify. Okay. So, let me take a very simple example, say I have this and then there is a if else. Okay. So, there is a if else like this, and here you have a loop and the loop has say 2 state and it is coming like this, and then you have the end state. Okay. So, if this is the behavior and there is a back edge from here as well, okay, how many paths will be there. Okay. So, let me give the name is say S1, S2, S3, S4, S5, S6, S7, S8, S9, S10, S11, S12, S13, right. So, I am going to remove this back edge. So, the back edge is basically loop 1 is S13 to S8. So, I am going to remove this, right. So, I am going to remove this and I am going to remove this one also. So, I have another loop which is loop 2, which is from S11 to S1. So, this information I will remove. Now, you can see this is my modified behavior, right. So, how many paths are there? So, basically I have path 1 which is basically S1. So, it will take like this. So, let me just draw properly. So, path 1 is basically this S1, S2, S3, then it will go to S4, S5, then S7, then it will go this way, right. So, S8, 9, 10, 11, S11. So, I have one path like this and we will have another path like this as well. So, that was missing earlier, right. So, I have path 2 which is basically again this S1, S2, S3, S4, S5, S7 and this is S8, S9, S10, S11. So, my path 2 will be similar, but from S8 it will go to S12 and S13. Okay, this is my S8, it will go to S12 and S13. Okay, S12 and S13. So, basically when you come from here, one path will be like this and one path will be like this. Earlier, since there is no state word, this was missing. So, similarly when you come through this, you will have one path through this and we will have one path through this. Okay. So, there will be P3, P4. So, which is I am just drawing it quickly. So, this is my S8, S9, S10, S11. So, this is this path and there will be another one which is P4 which will come like the same way, it will take the else branch and it will take the loop path, right, S12, S13, S12, S13, this is my S8. Similarly, so there are 4 paths and from this point, because I have to start path from loop point, there will be 2 paths, this one and this one, right. So, P5 will be S8, S9, S10, S11 and there will be P6 which is S8 to S12 and S13. Okay. So, there will be 6 paths. So, here in this is the same structure, I obtained 3 paths because from the loop point the loop body was missing, right. So, I have only considered one path here. So, but if we consider there is a loop point, it will become 2 and for these 2 paths again it will multiply with this path, right. So, basically there are 6 paths. I hope you understand this point, right. So, the point here is that given this program I represent this as a CDFG and then I am going to identify all the longest path. So, if the behavior is like this, it will have 6 paths and it is a similar behavior, only thing is that there is no content in the loop body, I will get 3 paths. Okay. So, this is what we have already identified. Okay. So, the next is the AFAP algorithm. The first thing here you should argue with me that why we need any new algorithm, because I have one path, I understand, I have one path. So, what I can do, I can just put all the operations of that path sequentially and do a scheduling, the list based scheduling, ILP or say force directed scheduling, whatever we have already discussed, we can actually apply them. Why we need a different algorithm? So, let me justify why we need a new algorithm called AFAP. Okay. The first thing is here, obviously the objective is to minimization of the number of control state overall, and specifically here we actually apply operation chaining. So, if you just think about this force directed scheduling or list scheduling, operation chaining is not considered and adapting operation chaining there is little bit difficult, because I do not know how many operation chaining can be done, right. So, that something is the first reason, and the second reason is most important is say for example, suppose you have a operation A equal to B plus C, and then you are doing say D equal to A minus 5, and then again you are doing A equal to say x plus y. Okay. So, basically this A get redefined. Okay. So, in that kind of, so there is a dependency, it is a read write after write, right. So, this is called write after write dependency. Okay. But that kind of things is not captured in basically in sequence graph, and as a result if you schedule them in two different timestamp it is fine, but if you schedule them in same timestamp it will create a problem. Okay. So, because you cannot update one variable two times in a single clock, right. So, you have to schedule this into two different timestamp, but if you just think about a sequence graph this may not be reflected, you have to add this kind of things there as well. So, and specifically, so in this particular AAP algorithm these things are already taken care very efficiently. So, that is why here instead of applying the normal basic block based algorithm, I am going to apply this algorithm called AFAP. Okay. So, what are the steps in the AFAP algorithm? So, what is the input to the AFAP algorithm? You have it will take one path at a time, right. So, it will take one such path, path means all the operation in the path, and it will give you the minimum number of control state where so to schedule all these operations, and this is basically very conservative approach here. It is initially assume that everything can be done in one control state. Okay. And then you think is it possible to do everything in one control state? If not, what is the problem, what is the things is causing problem, and you try to satisfy that constraint. So, and you try to increase the number of control state minimally, so that things can be done in minimum number of control state. Okay. So, what is done here? So, as you understand that you have to identify first all the constant, right. So, what are the constant among the operations, that you have to figure it out first. Okay. So, I will talk about them in detail, and once you identify the constant you find out that minimum number of states that actually satisfy all the constant. Okay. So, that is the next step. So, you identify the min cards, I will talk about what is min cards needed to satisfy all constant by apply graph coloring or max click finding algorithm. So, I am going to talk about that. Okay, do not worry. So, let us first identify what are the constraint to be satisfied. Okay. So, in a path, because in the path there are many operations, right. For example, this path has 11 operations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 operations. Okay. So, there are 10 operations and I want to identify the minimum number of control state to schedule this 10 operations. So, the first constant is variable constant. Okay. So, as I mentioned that one variable can be assigned only once in a control state, right. The example that I have just taken, that A equal to B plus C, then you are doing D equal to A plus 5, and then again you are doing A plus A equal to x plus y. So, it is possible there may be some operations here and there. Okay. So, see, so finally what is going to happen, this A is going to store in some register in the hardware, right. So, and now if you assume that I am going to schedule everything in one clock, what is going to happen? You try to first update this register with B plus C, then you try to update with x plus y in the same timestamp, which is not allowed, because you cannot update, because that update of the register is going to happen at the next clock, right. And say if you try to update twice, it will actually create some problem, because it is create some race condition. Okay. So, basically the first constant says that if one variable get redefined, you cannot schedule that two operation in the same steps. That means you have to break somewhere here, right. You cannot do these two operations at the same time. Okay. So, that is what is the first constant, that variable can be assigned only once in a control state. Okay. So, that means you have a path, you identify is there any variable is getting defined twice, and if it is getting defined, you have to break the whole path between these two, right. So, you can assume that I can actually execute everything in one clock. Now, because of the variable constant, I understand that this cannot be done one, you have to cut the whole path in two time, and then the first path is one state and the second part is another state. Okay. So, let me take the example that I have taken, so and then explain this. Say for this behavior, is there any variable constant? Yes. So, suppose you take a path 1. Okay. So, path 1 is this. You can see here I am updating PC in line number 5 and again in line number 9. So, that means I am updating this PC at line number state in line number 5 and again in line number 9. So, as I mentioned that these two cannot happen in the same state. So, initially assume that the whole path can schedule in one control state, but now I understand that no, it is not possible. So, where to cut this path? I have to cut the path anywhere between this, from this here to this, right. So, because after this you can cut here itself, but there is no problem if you cut it here, right, or you can cut here, or you can cut here, because even if you cut here, these two operations will be in two different time steps, right. So, that is what is called the variable constant, and you basically mention this constant as a bar. Okay. So, you are saying that essentially that since operation 5 and 9 is two operation which is updating the variable PC, I have to cut this path somewhere between 6 to 9, which is given by my this constant Vc constant, Vc 1, so that this variable constant is getting satisfied. So, if you assume that, so you can, as I mentioned, that you can cut at 6, 7, 8 and 9, but wherever you cut it satisfy my constant. Okay. So, this constant I represent by a bar, because there is a multiple option to cut. So, I am going to choose this latter. I do not take a decision at this moment that I am going to cut 6 or 7 or 8, but I represent the range where the path must be cut to satisfy this variable constant. Okay. So, this is variable constant. So, so you can have many such constant, but I just for our example I have only one such constant. Okay. So, the next was the resource constant. So, as I earlier also clarified that if there are say 20 addition operations, and if you schedule all 20, you need 20 adders, right. But it may be that you do not have 20 such adder available, so you have say 10. So, you have to cut the behavior such that in every state there are 10 operations. Okay. So, basically the constant says that you can only execute some operation in one state as long as it satisfy the resource constant, right. So, first thing is the resource constant is get satisfied, and the second point is that you cannot reuse the one function two times in a state, that is very obvious, right. So, if there is one adder, it has to be I can do only one operation at in a state. Okay. So, the resource constant basically clarify both things, that you use the adder in once in a state, and you actually satisfy the resource constant, right. So, basically satisfy the resource constant. Right. So, this is the resource constant. So, if you now take our example and say I have only one adder available, right. So, this is my resource constant, there is only one adder available, and see how many addition operations are there. So, if you take the path 1 again, you have one addition operation and one addition operations. So, there are two addition operations. Okay. And if I assume that, so I cannot do these two additions in the same step. So, because if I one function unit, I can only use only once, that is my resource constant. So, I have to add a constant between after 3 and before by 9, right. So, my next constant says that, so this is my, so if you just now think about this, so this is my 3 which is addition operation, and this 9 is another addition operation. So, I have to cut somewhere between 4 to 9, right. So, this is my range where I should cut. So, that is my resource constant 1, that you can cut at 4, you can cut at 9 also, because cut at 9 means you cutting here, right. So, 9 will be go to the next time step. Okay. So, effectively this is what the resource constant you are saying, right. So, now if there are say, you can understand that if there are say 4 such addition operation and only one adder, you will have many resource, right. So, you have to satisfy any pair, you have to cut, right. So, here I am taking very simple example. So, only one constant, but you may end up say just think about this is also plus operation, this is also plus operation, this is also plus operation, this is also plus operation. So, there are 4 operations and say I have only one adder. So, that means all these 4 operations cannot be scheduled in one timestamp. I need at least 4 timestamp to execute this, and in the constant I will identify one constant between these two, I will constant one constant between these two, and I will also identify one constant between these two. So, there are 3 constant to be added here, right. So, and obviously you can think about there must be some constant here to here, but because these two constants satisfy this, so I do not need this. So, the point here I am trying to cover that is that resource constant may add many such constant, right. So, this kind of constant you have to add for all possible resource conflict. Okay. So, this is what is my second constant. Okay. So, I have discussed about the variable constant, I have discussed about the resource constant. Okay. So, now what is the third constant? The timing constant. So, as I mentioned that operation chaining is something is the default option in timing this path based scheduling, because here I want to schedule everything as fast as possible. So, whenever there is no timing conflict, right. So, I am going to meet timing, I am going to allow the operation chaining as much as possible. So, by default I will assume that everything can be all whatever the chain of operations are there, I can schedule in single clock as long as it meets my timing constant. So, for example, say there is a adder chain is like this. Okay. So, I am doing say A plus B, then this is C, and then you are doing say D plus C, and then you are getting E, and then you are doing E plus F, you are getting G, and then say you are doing again a plus operation which is say G plus H, and you are getting say out. So, there are 4 such operations in chain. So, it will create a chain of operation in my behavior, because that is how I have explained, and by default I will assume that all 4 can be done in single clock. Right. Now, assume that this all every adder is 10 nanoseconds, right, taking 10 nanoseconds to execute, and if your target clock is 30 nanoseconds. So, it says that this 40 nanosecond, this path length, if you do a chaining of 4 addition, it will create a path length of 40, but your target is 30. So, your timing constant not met here. So, you have to break this path, and where to break? You have to break either between this here. So, you have a constant between this third and fourth operation, or you can also can break here, right. So, you just break it here, then this part you do, or you can break here also, because you just do 2 operations in clock 1 and in the next 2 operations in clock 2, right, in state 1 and state 2. So, there are many such constants going to happen. So, if you just take this example, how many constants will have? I will have 3 constant. One constant says that you break between this third operation and fourth operation, and you execute first 3 operations in state 1 and fourth operation in state 2, or you break between this second and third operation and say that first 2 operations execute in state 1, third and fourth you execute in step 2, or you break it between 1 and 2 and say that I am going to do only 1 in state 1 and 2, 3, 4 in state 2, all are valid, right. So, for this timing constant you have to add this kind of constant. In our example there is no such timing constant, because these are all only one addition operations are there, all are assignment operations. So, there is no timing constant for this, but you actually can have many such timing constant. Okay. So, what I am going to get after these 2 constants? So, I will take a path, because it is taking one path and schedule it. So, I am going to take a path, and the path is longest path, and I identify 3 kind of constant. The first constant is variable constant. Is there any one variable getting redefined? You break it in between. Is there any resource, is there any long path which is not satisfying my resource requirement? So, you break it in between, and also you have any timing violation. So, there is a chain of operations, is it violating my timing constant, then you break it, and you break it all possible way, so that it actually satisfy my timing constant, right. So, once you have all this constant, what is my objective? My objective is to identify the minimum number of state which you can satisfy all the constant. So, here I am going to talk about the state is now by cut. So, the point here is that, so the problem statement here is that I have given the constant is given by this bar, because it is not a single state, but it is a range of state where I can break the path. So, I have such constant, and I need to break the path into minimum number of times, so that all my constant get met, right. So, that is my problem statement now, and this is what is a very important problem and interesting problem. So, if you just think about my graph, which is very simple. So, I have one constant variable constant, which is this, and this is another constant. So, if you just cut anywhere between this place, this both will satisfy, right. So, I do not have to. So, if I just cut somewhere here, again I have to cut it here. So, this is a redundant cut, I do not need to cut here, right. To satisfy this both the constant, I have to cut somewhere between this 6 to 9, right. I should not cut at 4 or 5 to meet my resource constant. Then I have to again another cut to satisfy my the variable constant. Okay. So, the point here that, as I mentioned, that the problem statement here is that given the constant, you identify the minimum number of cut or the range. One cut is a one range where you can cut, and such that the minimum number of cut ensures that all the constant will be satisfied. Okay. So, if I take my example here, so obviously I had a cart here, you have to start something here. So, this is my state 1 and I have to cart somewhere between 6 to 9 and that is given by this, right. So, suppose I decided to cart at node 7, right. So, what does it mean? Abruptly that I am going to execute this part of the behavior in timestamp 1 and I am going to execute this part of the behavior in timestamp 2, right. I need S1 and S2. You can understand that there are 10 operations and at least for my example I need only 2 states. So, that is the benefit I am going to get through path based scheduling. Here actually the number of states gets significantly reduced because my objective is to minimize it and I am going to do as much of operation chaining, as much of sharing, as much of operation chaining, as much of resource operation to be executed in term step as long as they does not violate my resource and timing constant and variable constant. Okay. So, here I understand that for this behavior for one path, I understand that there are 2 constants and to satisfy this constant I have to somewhere cut between this and if I cut it here effectively I have 2 states. In state 1 I am going to execute all operation from 1 to 6 and in second timestamp I am going to execute all the operation from 7 to 10, right. So, this is understood. So, this is manually possible because there are only 2 constants under the 2 such bar, but if there are say 100 such bar, identifying this manually is not a way and specifically I am assuming these things can be done by a software, right, a high level synthesis tool that I am going to do it. So, how can I automate this process? So, that something is to be understood, right. So, how to automate this process is very interesting. So, what I am going to do, I am going to construct an interval graph. Okay. So, and then let us try to understand what is the interval graph. So, in the interval graph each such constant will be a node, right. So, each such constant will be a node. So, I have one constant VC1. So, this is node 1, I have constant 2, the resource constant 1, this is my node 2. So, the number of node in the interval graph will be the number of such constant. Okay. And now, I am going to add an edge here if these two have a overlap, right. So, if there is, since these 2 constants are overlapping, so I will have an edge. Okay. So, this way I am going to construct an interval graph from this constant. Okay. And what is my objective? My objective is to identify the minimum number of carts that satisfy all my constant and that can be done using clique partitioning problem, right. So, what that you identify the clique is complete subgraph. Okay. So, you identify the complete subgraph in the graph in this particular constant graph or interval graph such that all the nodes are getting covered by one of the complete subgraph and there is no overlapping. Okay. So, let me take an example of such. So, this is a very simple example. So, I need only one cart. So, it says that this is a complete subgraph, right. So, complete subgraph means it's have all the edges with them, right. So, this is my cart 1. So, it says that you need only one cart to satisfy both the constant, okay. And that cart I can identify by the common part in these 2. Okay. Now, let us take a very complex say my constant graph become the interval graph become like this. So, now you see here I identify there is a complete subgraph here, right. This is my one complete subgraph and then in this subgraph I have 4 nodes. So, what I am saying that you can actually have only one cart 1 which will satisfy all these 4 constants because they are all compatible to each other, right. So, if they are all compatible to each other, so I will have one cart 1 to satisfy this. And since this is one cart and this I need another cart here which is also a complete subgraph of 2 nodes and this is my cart 2. And I should not consider this cart of 3 because this is already taken care by this. This is also a complete subgraph, say this is of node 3, but I am not going to consider this because this node is already taken care by this cart 1. Okay. So, the idea here is that if you identify a complete subgraph, that means this all nodes are overlapping each other. So, all of them are overlapping to all of them. So, I can actually have one cart to satisfy this. Okay. So, if you ask me how to do it automatically, I am going to do it, I am going to construct an interval graph from this constant where each node represent one node in this interval graph, each constant, and if 2 constants having overlapping, then I am going to add an edge. And once I have that, I want to identify the maximum subgraph which is a complete graph, right. Complete graph means they have edge between all of them. and if there is a complete subgraph where everybody is connected to everyone, that means they are all compatible to each other. So, that means they can one single cart can satisfy all this constant, right. So, I am going to add only one such cart to satisfy all these constraints. Similarly, I am going to identify the other set of such complete subgraph, and for each complete subgraph I am going to add one cart, right. So, this is how I can actually automate the process. Okay. So, this I have to do it for all paths. Okay. So, I will take path 1, I will identify the constant, I will create the interval graph, and I will solve it, the click partitioning problem, this is called click partitioning problem, and then I am going to find out such clicks, and each click is one cut, and from this 4 node I will identify what is the common overlapping time, and that will be my cut. Okay. This is how I can do it for all one path, and I have to do it for all paths. So, this is done for path 1, and I identify that I need 2 cuts, right. So, one cut is from here and another cut is like this. So, basically what says that you basically cut between path 5 to path 9. Okay. So, now if you take path 2, because there are 3 paths we have identified in this behavior. So, in the path 2 how many constants are there? So, in the path 2 you see it is go through the else branch. In the else branch there is no this P c equal to this, right. So, this variable assignment constant is not there, but only this addition constants are there. So, there is only one constant. Okay. So, this cart is very simple because it has only one node. So, I am going to have a cart here and one cart is from this to this, right. So, I can cart anywhere between this. Again I need 2 state to execute my path 2, and this second state can be cart anywhere. Okay. So, that is for path 2, because in path 2 I do not have any variable constant, this is because this is not there, right. So, this is within the if branch and that is not in the else branch. So, I have only one resource constant, and I understand that I have one cart 1 and this is my cart 2, and this is what I obtain. And for path 3 there is no constant, right. So, if you just look into this code, in this part of the code there is no variable constant, no variable be defined twice, there is no adder constant because I assume there is only one adder available, which there is no addition constant, and there is no timing constant as well because there is only one addition operations. So, for this I need only one cut, right. So, basically it says that I can execute the path 3 in single clock, right. So, that is what the interpretation of this cut. Okay. So, I have 3 paths. For each path I identify what is the minimum number of cuts there, satisfy all the constant, and once I identify that information is ready with me. What next? So, obviously these 3 paths are not independent, right. So, you can understand that in this behavior these paths are actually overlapping, the significant portion of the paths are overlapping. So, I cannot say that I will create 2 paths for state 1, 2 paths for state 2 and 1 path for state 3, and I will have 5 state in the my combined graph. This is not true, right. So, what I have to do now, instead of doing that I have to combine this path. And how should I combine that? So, basically if every path has different number of timestamp, right. So, say my path 1 may have say 3 timestamp, path 2 may have say 2 state, and say path 3 may have 3 state. I have to create a combined one, right. So, I have to combine this state into a single FSM from this path, right. That is my next step. So, that is a overlapping of paths. So, how we can do that? So, my objective here is that I already identify the carts or the number of states in the each path. I have to combine these paths into one, and it is basically problem of finding minimum number of state for all path is equivalent to finding the minimum number of start in the find the minimum set of non-overlapping cuts. Okay. So, what I am going to do it now, I am going to use the same concept whatever I used to solve this, identifying the minimum cut to satisfy all constant, right. So, now if you look into this graph, what I have path 1, I said that I have to cut the path definitely at start and somewhere in between. I have path 2 and I identify that this path 2 has to be cut at this point and somewhere in between here. Okay. That is what we have already identified, and path 3 has to be cut here. So, you can understand this is more similar to this constant solving problem, right. So, for constant solving what we have done, we actually construct an interval graph and identify a click which actually says one click is one state. So, here I understand that path 1 also need 2 state, this also need 2 state, this also need 1 state. How many total number of states are there and how we can actually combine these states. So, the similar strategy, because this the graph looks like and the problem looks like the similar, I can actually apply the similar type of things here. Okay. So, what I can do, I can again construct a conflict graph or say interval graph. Okay. So, what I am going to do, for each cart I will have an node here. So, how many carts are there? 1, 2, 3, 4, 5. So, I will have a graph where there are 5 nodes, right. So, this is corresponding to this one, this corresponding to this one, this node corresponding to this one, this node corresponding to this one and this node corresponding to this one. Okay. So, I am going to construct this and you can understand that it is a similar problem earlier, that if there is a complete subgraph. So, this is a complete subgraph of 2 nodes, right. So, that means if I add one state here, that will satisfy both, and which is obvious. So, that means I am going to start a state which is starting from node 1. Okay. Now, this is interesting here. So, I have these 3 carts and you can see here they form a clique. This is a complete subgraph of 3 nodes. So, that means if I just add one state here, that will satisfy all this constant, right. And what will be the state? You can see here I can break this path 1 anywhere between 6 to 9, I can break this path 2 anywhere between 4 to 9, I can break the path 3 only at state 7. So, the common solution is state 7, right. So, I have to cut the path in state 7 only, because these 3 can be then this all these 3 cart can be satisfied by this, and that is my final solution. So, what I obtain, that finally I am going to break these paths into 2 state, my S1 and S2, and S1 is going to execute this part of the behavior and S2 is going to execute this part of the behavior, right. So, this is what I have decided so far. Okay. So, obviously, there are other part is left, that how to add transitions, how to put the operation into state and what will be the condition for this operation to be executed. So, these are all things to be discussed, but I am going to conclude today here with this note that that I will take the behavior, I will identify the CDFG, I will identify all the longest path, and for each path I am going to identify what is the minimum number of state needed, that I am going to do, and then I am going to combine all the paths states together, and for both the problem identifying the minimum number of state in for a path and identifying the minimum number of states to satisfy all the paths, the problem is resolved or the solved using the process clique partitioning problem. Specifically what I was doing is basically for either from a constraint or from a cart, I will construct a conflict graph or interval graph, and then identifying a clique is specifying that these conflicts or the carts can be satisfied by a single state, and then each such clique represent a state. Okay. So, this is how I decided that for my program, where it has a loop, there is a if else, there is a while loop inside, for everything I can schedule the whole behavior in 2 state, right. So, earlier it was if you just think about the same program, probably you, so if you just think about this program, so this probably needs a 2 state, this needs a 1 state, and this say need 1 state, this need 1 state, this need 1 state, right. So, because these are all loops. So, 2 plus 1 plus 3, 4, 5. So, you need at least 5 state to get the complete schedule if I go by basic block based scheduling, but here I can understand that everything can be done in 2 state. So, the number of control state obtained by this path based scheduling is minimal, right. So, I conclude here. In the next class I will continue this discussion of path based scheduling, where I am going to talk about what are the operations to be put in every state and what will be the transition, what will be the condition of the transition, and how we will generate the data path. So, that part is to be discussed in the next class. Thank you.